All right, so let's begin again with announcements. Homework 6 is on Piazza, and it's due Friday, so in 1 week's time on October 23rd at 11:59 p.m. Eastern on Gradescope. Studio 5 has been posted on Piazza, and it is due in 2 weeks. So Wednesday, October 28th. And as usual, both the Gradescope submission as well as the TA or undergraduate student assistant checkoff is required for Studio 5. The studio itself is based on decoders and encoders that we are going to learn today and in the next class. And a Studio 5 information link has been posted on Piazza for you guys to review. That will help with the Studio 5 issues that you may have. Quiz 12, our daily quiz, is on Gradescope. Please do that today. And it has 2 questions that were given on the exam in which the average was very low in the 50s. So I have assigned that again as part of quiz 12 so that you guys try to correct the errors in understanding going forward. Exam 1 grades have been posted on Gradescope, and I want to spend a little bit of time talking about the statistics and also some issues, and then I'll take your questions about regrade requests. So the statistics of the exam are being shown on your screen. This is for all students who took the exam, and the average, most of you might be curious about that. It is a low 80, so 81.2. There were a good number of students above 90 mark, a lot of them between the 80 and 90 points. This is out of 101. What else? Let's see. The maximum was 100, which means out of 100 points it was 99. The median of the exam was 83, standard deviation of 11.7. Now, let me talk a little bit about what I'm worried about. I'm really not worried about students who have scored more than a 70, especially people who have done really well. I'm really happy to see those high points. However, I am a little bit worried about this section right here. So there were, say, 4 students that were below a 60 mark. Now, I don't know whether these students are planning to drop the class, but if you're not planning to drop the class, please set up an appointment with me to discuss how we can improve your grade going forward in the class. So that's below a 60-point mark. Now, between a 60 and 70, there are still a good number of students, about 15 in that zone. I'm not worried about you guys, but I think that you guys need to do a little bit better for the next coming assessments. So try to push up your score for the next assessments. And for those of you who have scored really well, you guys need to work hard to keep it that way. Questions about the statistics? Okay, so it doesn't look like you guys have any questions about the numbers here. Let me go back and talk about regrade requests. So for regrade requests on exam 1, you have 1 week to do this from today, 1 week from today. So that's October, let's see, 23rd, right? Yes. And you have to email me at meme2@rpi.edu. And in your email, explain the reason why you think a regrade is justified. So explain me the reason why you are asking for a regrade request, and then I will go look at your problem and try to resolve that issue. Now, I should say that the partial credit rubric that the TAs used to grade this exam was consistently applied to all students. So when you ask for a regrade request for partial credit increase, that might not be resolved the way you hope for. But in the case of a very obvious mistake, maybe the TA accidentally put your answer as incorrect when it was clearly correct, please let me know and we can fix that. And you have 1 week to do this. Now, where do you look for solutions? Where the solutions are on Piazza under exam 1. Take a look at that, take a look at your answer, compare your answer with the solution, and then if you think that a regrade request is warranted, email it to me in 1 week. Let's see. Do you guys have any questions about regrade requests? Okay, let's move ahead. Oh, so I also want to point out something that is not very pleasant. There are a few cases in which we have evidence that the students might have copied from other students, and I'm looking at that. So I will be reaching out to students when we are sure that something copying related or academic misconduct has happened. But there are a few cases in which we think it did. All right, let's move on here. We talked about the statistics. Now let's get back to our combinational logic design part 1 lecture. In the last class, we were talking about timing diagrams, documentation standards, how should your schematic look like, what all information is provided on a schematic diagram in terms of pin numbers, reference designators, the title block, and so on. We also talked about active high and active low signals. And now we are going to start talking about uncertain propagation delay and causality in combinational circuits. So on the in part A here, we see a block which has some combinational logic design inside it, but it does have two inputs, go and enable. So these are my inputs here on the left side. And on the right side, I have the outputs of that particular combinational logic design, ready and data. So because it's a combinational logic design, the change in input is going to appear at the output after some time. And that time is uncertain. How do you represent that uncertain propagation delay on a timing diagram? So that's the question here. So as you can see in part B on this slide, you have go and ready signals. So go is your input, ready is an output, and data is an output as well. So you have one input here and two outputs. Let me highlight the input in yellow and the outputs are in blue. So the change in go signal is reflected in the change in ready and data after some time. And that time could be static or it could be uncertain. In this case, it is fixed after t sub r dy. So for example, if I use this particular time marker as t1 and say this is t2, sometime t2, and let's say this is t3 and say this is t4, right? Sometime, because the x-axis over here is time. That's the reason why we are calling it a timing diagram. So the change in go signal causes a change in RDY or ready signal after t2 minus t1 seconds. So that's the causality, right? So this arrow over here is showing that the change in go has caused a change in ready signal after that amount of time, t2 minus t1. So we can write a statement over here to explain that. So you can say change in go caused changed in ready. That's the causality aspect of signals. Now, in a similar manner, that change also happens over here. So as go signal goes from high to low, there is a change in ready signal going from high to low after a certain duration of time. This might be the same as t2 minus t1, or it might be different. So the rise time and fall time of signals, they are very close to each other, but they are not necessarily exactly the same. In a similar manner, the change in go also causes a change in DAT, the data signal, after t sub DAT. So if we had this amount of time, say you can maybe call this t5. So t5 minus t1 would be the propagation delay between go and data. And similarly, you have it for the other case as well, which is what, t4 minus t3. You have that propagation delay again. Now, sometimes that propagation delay is uncertain. So how do you show that on a timing diagram? We show that with a min and max value. So for example, over here, the change in go has caused a change in RDY, and it's a range of propagation delay. So there's a minimum for that and a maximum for that. So we show that in this form, indicating that the change could have happened anywhere in this time region. Similarly, you have the four other places where we show that uncertain propagation delay with a minimum and a maximum time. So those would be the limits on the propagation delay, the uncertain propagation delay. Now let's talk about data transfer from, say, one point of the circuit to another point of the circuit. We are using over here data in as something that we are using as our data input, and we are writing that data to another place in the circuit, which we are calling as data out. So these are, this could be a part of the memory with data in and part of the memory at a different location in data out. Now, when you want, or data in could be coming from an external port, an input device, for example. But whenever you want to write something, you would use a control signal. In this case, we are using an active low control signal called write underscore L. That means, using our background on active low and active high signal, we can say that when this is low, that actually means we are writing. And when this is high, that's when it is inactive, which means we don't write then. And as you can see, for the initial time, that signal write underscore L is actually high. So that's inactive during that time. We are not writing anything to our data out. But when it goes low, we see a change in data out. And that change is essentially take the contents of data in and then assign them to data out. However, one thing that you must be careful of is that during that change, the data in itself has to be stable before and after the write underscore L changes. So before that, it is called the setup time, and after that, it is called the hold time. So the data must be stable in order for you to copy that over to data out properly. Otherwise, there will be a corruption in the writing process. So let's define what is T setup and T hold. You will hear this term T setup and T hold many times over the course of the semester. Right now, we are talking about this in terms of combinational circuits, but you will also hear it when we start talking about sequential circuits in which there is memory. The definition will be the same. T setup is the minimum time for which the data input, DATA in, the data in has to be stable. It cannot change during that time before the control signal write underscore L is active. So you see the time at which it becomes active is right here. And before that time, there is some small amount of time that we are calling as setup time. In that time period, data in cannot change over here. It has to be stable during that time. And that's what we are calling T setup. In the same way, T hold is same definition, but instead of before, it is going to be after. So I can take this definition from here, copy it, paste it over here, maybe do a color change in red, and over here it's going to be minimum time for which data in has to be stable after the write underscore L is inactive. So those are the two things that we changed here. We changed that and then we changed that. So before and after you activate your control signal, which is in this case is write underscore L, the data has to be stable. Only when the input data is stable, it can translate to uncorrupted data out. In a similar manner as before, we are indicating the uncertain propagation delay by using these two causality arrows. So we have got this causality arrow from here to here, and that's it, right? There's only one change there because after that there is new data in there. There is a T out minimum and T out maximum. So there could be a range of time in which that control signal takes effect as far as the output is concerned. So it's the same discussion about causality and uncertain propagation delay as before. So if we do this correctly, if we do the data transfer from data in to data out correctly, before that transfer happens, there is the old data. And after we make this control line active, which is right here, data from data in gets copied over to data out, but it could start anywhere from this time or to this time. But after this time, it has to be data in. Whatever is data in is over here, and that's your new data. In a similar manner, we can also show another timing diagram over here, in which instead of having signals that can only take one value or the other, we are showing that we are showing a bus timing diagram, and that bus is 8 bits long. So for example, we have a clear input signal. Clear is an active high input signal because you can clearly see that there is no underscore L indication here. So that's an active high input. So when it goes up, that's when you are saying, I want this to get cleared. And you can see that the step, which is your output, gets cleared because of that. So you can actually draw an arrow like this. The clear signal, when it went from low to high, caused a change in step, which is 8 bits long, 7 down to 0, to go to 0, 0, right? It got cleared. That bus is 8 bits long. So 0, 0, those are hex digits. They literally mean 8 zeros. And similarly, FF is going to mean 1, 1, 1, 1, 1, 1, 1, 1. So if you have another control signal called count, which is also an active high signal, when it goes up, every time it goes up, it causes the step signal to increment by 1. This is something that you will see in counters. When we design counters, you will see this signal that gets incremented by 1 every time it becomes active or after a certain duration. This count is, usually a clock signal. So it goes up and down at a particular frequency, and that will control at what rate the counter is counting. And the last one is an output, which is 8 bits, which is going from 0, 0 after it gets cleared, and it counts from that all the way to FF maybe at the end. All right. Now, to get a sense of what these uncertain propagation delays look like, let us take a look at a table that will give you a sense of, what is a typical value, what is the maximum value of propagation delay for a certain 7400 series IC. So in the left column over here, you see the part numbers of the ICs that we briefly talked about in the last class. So 7400, 7410, 7402, and so on. Then if that part number, if that particular IC was designed using 7/4 high-speed CMOS technology, then it could have a typical propagation delay and it could have a maximum propagation delay. The typical value over here, let me just talk about what this denotes. T sub PLH denotes propagation delay as the signal goes from low to high. And TPHL is propagation delay for an output when it goes from high to low. It could be 11. What? 11 what? This is in nanoseconds. So all these numbers in this table are in nanoseconds. So as you can see, the typical as well as the maximum propagation delays are very small, of the order of nanoseconds. But if you have slow signals, then nanoseconds don't affect you too much, right? So if you have things that are happening at the rate of kilohertz or megahertz, then nanoseconds is 10 to the negative 9. So that wouldn't matter. You wouldn't, try to fix for that or try to incorporate that in your design. However, if you have very, very high speed signals, maybe of the rate of gigahertz, which is 10 to the 9, then even the delays that are of nanoseconds order, they will start becoming significant. So you'll have to incorporate for that. So for example, in a scenario where you have 4-bit lines, 4-bit buses, you would have to route them on your printed circuit board in such a way that all 4 give you the same delay, so that all 4 things change at the same time at the input to the next gate. Similarly, you have all these numbers. These are just for your information. We will not be using them for doing any problems. They are just there to as a FYI. Like I said earlier, these numbers, they do not need to be the same. So for example, if you see over here, the propagation delay from low to high and high to low are different. Most times it is the same, but they don't need to be. All right, let's move on here and let's talk about programmable logic arrays, PLAs. So this is related to FPGAs. However, there are some limitations. The limitations that programmable logic arrays have is it is not as efficient as an FPGA. An FPGA allows you to have a really complex circuit in a very small amount of space. PLAs are a bigger set, and they don't have to be as efficient as FPGAs. But they do share the same property of FPGA, that any combinational logic function, can be realized as a sum of products. So if you have an array of AND OR gates, by programming the connections between the AND array and the OR array, you can implement any combinational logic function. Now, just to get a sense of, let me ask you this. Which other components have we seen so far in the course that can do this? Any combinational logic function. NAND and NOR, perfect. So NAND is in that list because it's universal. NOR is also on that list because it's universal. Now let's talk about sum of product. PLAs are using sum of products. Could I do a product of sum and implement any logic function? Yes, you're absolutely right. So POS is also an option. So NAND, NOR, POS. The reason why I am talking about this is because we are going to keep adding to this list. Because we are going to add decoders to this list. We are going to add multiplexers to this list. So we are going to learn in this lecture or in the subsequent lectures how we can use decoders and multiplexers to implement any logic function. Right now we are talking about programmable logic arrays. These are pretty simple. You have an array of AND gates and you have an array of OR gates, and you're just going to program what? The connections between them. And as you program the connections between them, you implement a sum of products expression. So for any combinational logic design, you need to talk about how many inputs can you have and how many outputs can you have. So over here, in general, we are saying that we have a programmable logic array with n inputs, and these are feeding into AND gates, because the first level of this circuit is AND. The next level would be OR. We not only have the n inputs, we also have their complements. So we have in total 2n number of inputs to these AND gates, true and complement of each variable. So for example, if you have A, B, C, D, you also have A complement, B complement, C complement, and D complement available at the inputs of those AND gates. So that makes it 8 inputs instead of 4, 2 times n. In terms of outputs, we have M in general. The outputs will of course come from the OR gates. So these are going to be driven by the large OR gates. Each AND gate, you can program that to be connected to each OR gate. Now, how many AND gates are you going to need? Well, we have another variable for that, small p. And obviously you need small p to be much less than 2 raised to n. Why is that? The claim over here is the number of AND gates you need in a PLA has to be less than 2 raised to the number of input variables. So for example, let's see, if you have 3 variables, then say A, B, and C, right? So the claim over here is you will only need less than 8 AND gates. Do you guys agree with that? Why do you think that is the case? Number of transistors. So why is this less than 8? Why is this not less than 4? Or why is this not less than 6? Why is this? That takes into consideration every possible combination of inputs. Absolutely right. So if you have all 8, then you might just have the function f equals 1, right? So there's no point of having all 8 AND gates. You will have a situation where you have less than 8. So the number of AND gates in your array should be less than 2 raised to the number of variables as inputs. Now let's take a look at an example programmable logic array. In this case, you have 4 by 3. So what is 4? What is 3? And then there are 6 product terms. So 4 corresponds to the number of inputs. I1, I2, I3, I4. 3 corresponds to the number of outputs. O1, O2, O3. So you have 4 inputs to the logic function, 3 outputs of the logic function, possible, 4 possible inputs, 3 possible outputs, and we are using the number of AND gates as 6 product terms. So we have used 6 AND gates. We had to be less than 16. We are way less than 16. We are 6. Now let's see how this is done. As soon as the inputs come in to the PLA, you have a inverter and a true form creator, right? So I1 goes in straight and I1 complement goes on the second line. I2 goes in straight, I2 complement goes on the next line. So that creates your 2 times n inputs. All those inputs feed into each and every AND gate. The AND gates themselves will have 2 times n number of inputs. The inputs are programmable. So when you see this X mark, that means that it is a programmable connection. You can have it or you can leave it disconnected. That's why the PLA is called PLA, right? There is a P in there, programmable. So that's what you're programming, those connections. Maybe I can highlight that in a different color, perhaps green. P is this. Those are the connections that you can program. What feeds into the OR gates and what feeds into the, what feeds into the AND gates and what feeds into the OR gates. All of that you can program. Each output of the AND gates feeds into the OR gates as well. So that's your AND OR array. AND level here and OR level here. So by doing this and just programming the, all right, so you're absolutely right. This hurts to look at, which is why we are going to start looking at a compact design. But so just bear with me for just a second. We will look at a simpler circuit in just a few seconds. So that is a 4 by 3 PLA with 6 product terms as a complete network. But it is not necessary for you to draw so many lines. As you guys have seen, this hurts to look at, right? So why draw this when you can draw something like this? This is also going to give you the same information in a very, very compact representation. You still have 4 by 3, right? So this is still 4 by 3 PLA with 6 product terms, the same PLA, but we have just reduced the number of lines because we are going to only focus on the cross connections. So instead of having all those cross connections in a serial manner, now we are connecting them in a matrix form, in an array form. Still they are programmable. That's why we are indicating the X. So using this compact representation, let us try to see if we can implement a particular logic function. Let's see if we can. Let me take an example here. How about we synthesize this? I want O1 to be I1 ANDed with I2, or I want complement ANDed with I2 complement, ANDed with I3 complement, ANDed with I4 complement. So how can I synthesize this O1? What kind of cross connections should I connect, and then which ones should I leave unconnected? Now, as we are doing this example, you will realize that there are many possible solutions. There are many possible ways you can do this. So for example, I only need, how many AND gates do I need here? The number of, do I need all the 6 product terms? 2, right? So I just need 2. So I could use P1, P2, I could use P1, P3, I could use P5, P6, I could use any 2, right? So many possibilities here for the right answer. Let us say that we are using P1 and P2. Let's break the pattern. Let's use P5 and P6. How many OR gates do I need? Well, I just need one OR gate, right? Because the O1 equals that product term plus that product term. There is only one OR gate that I need. And because it is for O1, I have to use that OR gate. So let us take a look at that. I want P5 to be this. And I want P6 to be this. P5 should be I1 and I2. So I would make that cross connection by making the connection here and here. That's it. Everything else I would leave unconnected. So that's how I get I1 and I2 for P5. For P6, I need the complements of each of them. So I would connect here, 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 and here. I got P6. And then for the connections to the OR, I would connect it there. And that represents my O1. Just with those, what is that? 2 plus 4 plus 1, 7 connections. That's it. Questions about this example? So I just took an arbitrary sum of products expression, and I implemented that using a 4 by 3 PLA with 6 product terms. Many solutions were possible, but I just used one of them. Oh, you're right. Yes, I need one here too. You're right. Yes. Well, I hope that you don't have to draw it. I don't think there is anything useful in just drawing it by hand. It's where you make the connections. That's what matters. Is P5 and P6 connected in series? P5 and P6 are the outputs of the AND gates. So they're all independent lines, right? So think of this. So think of it like this. We are used to seeing something like this, right? AND OR circuit. So all of this is kind of all of that. And then this guy is this. All right, let's move on here and talk about the same example for O1 is being shown here, but instead of using P5 and P6, you can see that the example over here uses P1 and P2. This is what we did earlier to get O1. We just used a different AND gate. That's how we did O1 here. But because there are two more possibilities for O2 and O3, you could also do O2 as I1 and I3 complement, or I1 complement and I3 and I4, or I2. So that's for O2. And then let's do the last one here, which is O3. O3 is what? I1 complement and I2 complement and I4 complement, or something that we had for O2, which is what? I1 and I3 complement, or something they had for P1, I1 and I2. Now this example should give you a hint that the PLAs are going to be very useful if some of the terms are common between the output functions, so that you can reuse them. You don't have to implement it again. That's what happened between O3 and O2, O1, right? O3 had some terms from O2 and from O1. So we were able to use the already implemented product terms. We were able to reuse them. So that's what increases. That's why we essentially need the number of AND gates to be much less than 2 raised to n. That's exactly the reason, because we can reuse some of the product terms between functions. All right, questions, guys? All right, let's move on to decoders. Decoders happens to be one of the more important combinational components of this course. It's very useful because, as I pointed out earlier, you can implement any logic function using a decoder. And it's a very interesting component. It has, in terms of inputs and outputs, you can talk about it in 3 different categories. Decoder, as the name suggests, it should decode, right? Like that's should decode. And if you have to decode something, you have to give it a code. So you give it a code and it gives you a decoded output, right? That's what a decoder should do. So your input code word, the code, that's an input. It could be 2 bits, it could be 3 bits, it could be 4 bits, it could be any number of bits. And then the decoded output, let me use blue for this. the decoded output is right here. That's your output code word or decoded code. And then there is another set of inputs that you could use to enable your decoder. Why? Because of two things. One, you may not want to decode things all the time. You may want to decode things only at a certain times, right? Only specific events. That's when you can use an enable signal to control when does it decode and when does it not decode. So that's one purpose. The other purpose, which is more clever, is if you wanted to put multiple decoders together, say for example cascade decoders, then you can use the enable inputs in a very efficient way to connect smaller decoders together to make a bigger decoder. And we will see examples of that. So three different categories of inputs and outputs: the code word, the output code word, and the enable inputs. The typical form of a decoder is n inputs and 2 raised to n outputs. So for example, 2 to 4 or 3 to 8 or 4 to 16. This is in context of inputs versus outputs. So 2 inputs, 3 inputs, 4 inputs, and for the outputs I'm using blue. 4 outputs there, 8 outputs there, 16 outputs there. So 2 to 4, 3 to 8, 4 to 16, or in general n to 2 raised to n. That's typically what happens. Doesn't have to be, but that's typically what happens. Now, to discuss more about the decoders, I like to talk about this. Suppose you are asked to decode a bit sequence. So for example, if I say 1 0 1 0 1 0. Actually, let me do one less. 1 0 0 1. If I asked you to decode 1 0 0 1, what would you guys say? Without any information, if I just said decode 1 0 0 1, what comes to mind? 9. Perfect. Right? So if this is a code and this is the decoded output, how can I design something that will take in 1 0 0 1 and that particular circuit has to output a 9? How can I do that? Well, here is where the decoder comes in. We would need, for this case, a 4 to 16 decoder. Why 4? Because our input code is 4 bits long. Imagine the 16 outputs to be LEDs. The 16 outputs, say, are LEDs. I'm just talking about decoders in this context just to explain what they do, right? We not always have LEDs at the end. But if the 16 outputs have LEDs, and because this is a 4-bit code, I have 4 inputs to this. What I can do is I can design my 4:16 decoder in such a way that when it sees 1 0 0 1 at the input, it lights up the 9th LED. Only one of them, but it lights up the 9th LED. You guys see that? All the other LEDs are off. 0th LED to 8th LED and 10th LED to 15th LED are off. Right? That's what I want this circuit to do. when you get 1001, you light up only one LED, which essentially is a circuit way to tell me 9, right? The circuit, obviously a digital circuit, a combinational component cannot tell me 9. It can indicate 9 by lighting up one of the LEDs. So the output of the decoder is going to be 2 raised to n, where n is the number of input bits. You got it right, yes. Is this how the segmentation display worked in Studio 2? Let's see, segmentation. What was Studio 2? Studio 2 was the 7-segment display, right? So 7-segment display took in 4 input bits and did a, well, so that was slightly different. That was, we used an array. So it was for the same kind of purpose, but we limited that to hexadecimal code, right? So we outputted a code which was 0 to 1, 0 to 9, and A through F. This is literally converting, this example is literally converting binary to decimal, right? That's what is happening over here. But because circuits cannot tell you 9, they are decoding that in the form of the nth LED, right? The 9th LED, for example. All the others have to be off. Now, let me ask you this. Do all the LEDs, do the remaining LEDs have to be off? Is it very important? Is it very important for the remaining LEDs to be off? Yes. Next question. Whose responsibility is it to keep them off? Is it the programmers? Because the programmer is going to say 1001, and the programmer can give anything, right? 1010, it can give anything. The one who is designing the circuit. Okay, so the circuit, right? The circuit itself is going to take the burden of that. So the decoder itself has to do that, right? So the decoder is going to take the responsibility to make sure that only one thing is active, only one output is active, all the others are inactive. So the responsibility doesn't fall on the person who is giving the input code. The responsibility falls on the person who is designing the decoder. All right. I hope you guys found that discussion helpful. What I'll do is, actually, before I do this, let me lay out the basics for the decoder from ground up. So I'll talk about a 2 to 4 decoder first. The simplest kind of decoder. 2 inputs, 4 outputs. Now for this, what I'll do is I will have 2 inputs and 4 outputs, obviously, right? 2 to 4. And I will call my inputs, say I1 and I0. So I0 over here and I1 over here. And then I will have, say, 4 outputs, 2 to 4, right? So 2 inputs are there, 4 outputs are right here. Y3, Y2, Y1, Y0. Now notice when I'm making this truth table for the 2 to 4 decoder, I'm using the subscript 0, 1, 2, 3, or for the inputs 0 and 1 to indicate least significant and most significant input and output. So 0 is the least significant output here, and Y3 is the most significant output there. I0 is the least significant input, I1 is the most significant input. So what are the, how many zeros and ones should I fill on the input side? It's a 2-input situation. So I will have 0, 0, 0, 1, 1, 0, and 1, 1. These are the 4 possibilities. Now, when it is 0, 0, yes, you got it right, 4. When it is 0, 0, what should happen to the outputs? Which one should be active? So Y0 should be active. Yes. So Y0 is active here and everything else is inactive, right? The one thing that I forgot to mention here is this. All inputs and outputs are active high in this case. No, 0, 0 should be decoded as 0, right? So that's Y0. And then when you go to 0, 1, what should happen? The next code, Y1. You got it right, yes. So this guy keeps moving left. That's the others are off. Yeah, absolutely. And in the similar manner, you can fill out everything else about this circuit. Now we said there are 3 things that can qualify as inputs and outputs to the decoder. One is inputs, the other is output code, and you can also have an enable signal. So let's put an enable signal as an input. En. So only when the enable signal is 1, it can do this. And when the enable signal is 0, it's disabled. No matter what I1 is and no matter what I0 is, it is going to give you zeros at the output. You guys see that? So when the decoder is disabled, it doesn't matter what I0 is, it doesn't matter what I1 is, all your outputs are going to be off, meaning no LED is going to be on. Now with this, let us write a logic expression for the outputs, because that's what we do in combinational logic design. We write the truth table. From the truth table, we write logic expressions. From the logic expressions, we draw out the logic circuit. So what would be the expression for, say, Y0? What logic expression should I write for logic Y0? This should be simple. Not A and not B. I think you mean I1 and I0, right? Okay, so what about enable? Enable has to be on as well, right? So my expression for Y0 should be enable and I1 complement and I0 complement. Yes, you got it. In the similar manner, I can also write an expression for Y1, Y2, and Y3. Let us write that down. Y1 is going to be what? En and I1 complement and I0. And Y2 is going to be what? En and I1 and I0 complement. And Y3 is going to be En and I1 and I0. Yes, you got it. Always include a column for En. You guys okay with the logic expressions here? Next, what is this? We know what are min terms and what are max terms. So can you guys tell me what these highlighted products are? Min terms, yes. So En ANDed with min term 0, En ANDed with min term 1, En ANDed with min term 2, and En ANDed with min term 3. Notice I used small m to indicate a min term. And that's it. That's your design, right? Now, let me put the note over here again. For this design, our inputs and outputs were active high. So the next question is, what if you want the outputs to be active low? What happens then? So what I'll do is this. I will copy this from here. And then I will add another slide, paste it over here, maybe make it smaller and have it over there. So the next question is, what if we want active low outputs? What should I do? Change it to not En, max terms. So min terms becomes max terms, that's good. Use max terms, is good. All right, so let's take a look at what happens. So all of you are right. Y0 would become Y0 complement, which would be what? En and min term 0 complement, which would be En complement or min term 0 complement, which is essentially En underscore L active low enable or max term 0. You guys see that? And because it is Y0 complement, I can simply write this as Y0 underscore L. So an active low output is essentially active low enable or max term 0. Now you can similarly write for Y1 underscore L and Y2 underscore L and Y3 underscore L, all active low outputs. Y1 underscore L is going to be what? An active low enable or max term 1. Y2 underscore L is going to be enable, active low enable or max term 2. Y3 underscore L is going to be active low enable or max term 3. Now let us identify what is the active level for inputs, outputs, and enables. Inputs are active blank. Outputs are active blank. Enable is active blank. Are the inputs I0 and I1 active high or active low? active high. Perfect. We didn't change anything about the inputs. We just wanted to see what happens when if we want active low outputs. So we didn't change anything about the inputs. Active inputs are still active high. How about the outputs? Outputs became low, active low. How about enable? So for this, you would need an active low enable, active high inputs, and active low outputs. If you guys have, just for your reference, I will also lay out the max terms here. M0, capital M subscript 0 is what? I1 or I0. Capital M subscript 1 is I1 or I0 complement. Max term 2 is I1 complement or I0. And max term 3 is I1 complement or I0 complement. All right, so I want you guys to kind of note what happened here. We converted the outputs to active low. It turned out that our enable signal became active low as well, but our inputs are still active high. And there is a reason why I discussed this particular case of us wanting to make things active low. The reason is one of the standard chips that have a decoder has that particular aspect. So when we start looking at that chip, which is 74X138, you guys should know the expressions and where it comes from. It comes from right here. All right, let's move on to the next one, which is this. So now we are going to essentially see in terms of slides what we have discussed already, right? So this is your binary 2 to 4 decoder, active high inputs, active high enable, and active high outputs. We have already talked about this. This is your 2 to 4 decoder block diagram. Inputs are here, enable is here, and outputs, 4 of them are to the right side. We have already laid out these details earlier. After we did that, we also wrote expressions for Y0, Y1, Y2, and Y3. Remember, we did this, right? Y0 is enable and I1 complement and I0 complement and so on. Those expressions are now implemented using 4 AND gates and 2 NOT gates. So for example, Y0, we can track this down. What is Y0? It is, let's see, this guy ANDed with this guy ANDed with this guy. So it is enable and I1 complement and I0 complement. Exactly exactly what we wanted. We looked at it before. And similarly, you can write for the other 3. So the 2 to 4 decoder logic diagram that is presented over here is just a representation of the logic expressions that we had derived for it earlier. It's the same one. Any questions about this? So this is kind of all are active high. When I say all, I mean inputs, outputs, enables. Now we move on to the case where we changed the, so how do we program something to be active high or active low? So we don't actually program it. We are actually looking for it. So here, the main question over here is, why would you want to make it into active high or active low? So this particular slide should indicate that. Earlier, we had 4 AND gates, and we know that using AND gates costs you more money and space than using NAND gates, which are universal. They actually use less transistors. We saw that earlier. So if I were to put a NOT operator or a bubble in front of the AND gates, I would literally get NAND gates. But I cannot just add a bubble. I also have to consider the outputs to be active low. So that's what we did over here. We complemented the outputs of the AND gates of the previous diagram, and we considered our outputs to be active low. Hence the name _L. And we also got our enable signal to be active low. So we used an inverter over here so that that happens. Oh. Now another crucial thing that we have incorporated over here is the fact that we are using more NOT gates than necessary. Now the question is why? Why use this? So for example, I needed A over here. So why not just use that? Why go through this guy and this guy? And the answer for that is input buffering. We saw that when you share a signal between many things, the fan out of the previous gate might actually affect that voltage for A as well as for B. Imagine A, this particular signal, 1A and 1B, coming from a different logic circuit. And those, if those signals are driving multiple gates, then because of fan in limitations of these guys and fan out limitations of the previous one, you might have a case where the logic levels at the inputs may actually not represent the desired level. In that case, you can use buffers. So that's exactly what we are using here. So 2 NOT gates back to back, that are essentially working as a buffer. So when you use a buffer, you are essentially solidifying that logic level, and now you can use it for more things. Does it make a difference where you put the bubble for the NOT gates? Well, in generally, when you want to represent something that cancels out, you put them on the same line. So for example, if you put something like this, it is the same as this. However, if I put it like this, it is very easy for me to see that these two cancel out. So it is just a matter of drawing symbols in which it is easier to track what cancels and what doesn't. But logically, no change. It is the same circuit. It is the same inverter operation. This buffer, or you can think of it like this. This is a buffer with active low output. This is a buffer with active low input. So if I combine those statements, that is, this is an inverter, this is also an inverter. So that's as far as the buffering is concerned, right? And then we have used NAND gates at the output. And when we use NAND gates at the output, our outputs became active low. So I hope now you see why we looked at the case of what if we wanted active low outputs. That's exactly it, to make things faster and use NAND gates instead of AND gates. So that's your symbol. That's your decoder symbol of a standard chip, 74X139. 74X139 is a decoder chip. It has 2 2 to 4 decoders. And because it has two of them, only one of them is shown here. That's why the half. So this is half of that chip. The complete chip is over here. Both of them are there. They are both independent. So for example, if I sketch this, this is 1 2 to 4 decoder, which is right here. Why are you being so difficult? Okay. And then the second 2 to 4 decoder is right here, which is right here. That they are both separate. They are not connected to each other. Is G underscore L enable? Yes, it is. Sorry, I forgot to mention that. This is active low enable. These are all active low outputs. And then active high inputs. Oh, actually, let's talk about this a little bit more. Which signal is the least significant output here? Least significant output. Y0 underscore L. Perfect. It is right here. This guy is the least significant output. Which one is the least significant input? Okay, is it A or B? How do we know? How do we know whether it is going to be A or B? Is there a way for me, like, if I wanted to find that out, how would I find that out? A is first to be on. Look at Y1 underscore L. It is on in Y1. Yes. So one of the ways is to track Y1, or you could track Y2, in which A and B are different. So for example, if I were tracking Y0 underscore L, I get A complement here and B complement there. So that's when both of them are 0, 0, right? And then that doesn't give me much information. And as Preston pointed out, if you look at Y1, the two inputs are here. Let's see if I can highlight this. This guy is coming from A, and this guy is coming from B complement. So if between Y0 and Y1, what changed? A changed. So A changed first. Is that right? So it has to be the least significant. So this guy is your least significant input, and this guy is your most significant. Earlier we were using I0 and I1, so the numbering was convenient. In this case, we are not using numbering, which is why we need to. What do you mean by changed? Okay, so the logic level, right? So you see this. Let me. If you look at this table, the input that changes the slowest is the most significant, right? So 0, 1, 0, 1. The thing that changes faster is least significant. If you take that to this, for Y0, I have A complement and I have B complement as the inputs. For Y1, what do I have? I have B complement, but I have A here. So A changed. You see that? That's why A changed first. No problem. All right. let's move on. So that's half of your symbol. Active low enable, active high inputs. A is least significant, B is most significant, active low outputs. So the chip itself has, just before it comes out, there is Y0, Y1, Y2, Y3 indicating active high here, but the bubbles are actually making it that active low. The complete symbol is over here. So you have 1 as the indicator, 1G, 1A, 1B, and so on, indicating that that's your first 2 to 4 decoder, and then 2G, 2A, 2B, and so on, indicating the second 2 to 4 decoder. So that's your complete 74X139 chip. Each of these is the same copy as before. We just saw this before. Everything is the same here, except that it's the second copy. Now, in terms of diagrams, in terms of symbols, we have to be a little bit careful. You see over here, we put G inside, and then the bubble was in the front. So there was only one inversion. That works for an active low signal. Over here, similarly, we said bubble, 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 and for active low, we are putting only one bubble, and that works. For active high inputs, we don't have any bubble, so that works. However, we cannot draw a symbol for the 74X139 with double complements. So for example, over here, we are putting a bubble, and we are also putting the naming as Y0 complement. That's a double inversion, so that's not allowed, right? But this is, so we have the way we have named it itself has complemented forms for the outputs as well as for the enable. So that works. The symbol for the 74X139 that we will be using is this. So inside the chip, you will see active high naming scheme. And then whenever you have active low, you put a bubble just outside that block. All right. What I will do here is I will stop my recording